Good afternoon, everybody. So the talk today is going to be by Dr. Sikarin Yu Kong on black hole information paradox simplified. Yes, welcome.
All right, okay. Well, thank you, Dr. Pichet, right, for asking me to give a talk. Actually, I have no intention to give any talk, but once you ask, it seems like I have to respond. Then I decided to give this topic as a talk. As you can see, this is black hole information paradox, but there is a word simplified, right? Okay, it means that if you expect some like huge computation from my talk, I'm so sorry, I don't have that. I have only like a cartoon version to explain things here in this talk. And then the black hole is not my expertise, but I do fancy this kind of topic. Then I follow the literature and I try to catch up the essential of the statement of the paradox. And then today I'm going to explain that in the simple way, okay? So, at the beginning, I'm going to give you some basic on quantum mechanics about what is a density metric, and then about the unitary evolutions, which is actually the heart of the quantum mechanics. Yeah? And then I'm going to explain how to quantify the entanglement, and then how to use Von-Neumann entropy, right, to measure the entanglement. And then we're going to talk about the Hawking radiation. And then after that, I'm going to point out what is the paradox from the Hawking radiation. And then after that, there is the solution for the paradox that we call the black hole complementarity. But you will see that for the black hole complementarity, will create you another problem, which is actually called firewall, right? That would be all for my talk, okay? Okay, so suppose I give you an ensemble of pure state here with a probability distribution. Yeah, all right. We know that actually the density metric can be expressed in this form, which is that we call mixed state right here. And then this we have the condition that some of the probability distribution has to be 1. Right. This is like the classical distribution. But if one of the p equal to 1, you get the pure state. Right, okay. And then the properties of the density metric. The first one is the density metric must be positive, right? Okay. And there is the density metric must be Hermitian one. This means that this property guarantee the real eigenvalue of the density metric. And the last one is trace of the density metric has to be 1. This is the normalization condition. Right? This is very simple. And for the pure state, we find that actually rho square is equal to the rho, then trace of the rho square equal to 1. Right? It's very trivial for the pure state. But for the mixed state, we find that actually rho square is not the same with the rho. Right? And then we find that rho square is less than 1, obviously. And then we can say that actually here, rho square can be used as the measure of the purity of your state right here. And then because if it's 1, your state is pure, but if it's not, if it's smaller than 1, your state is mixed. And then I can define mixedness of your system as, this one. And then somehow people call this formula as a linear entropy, right? Okay. And then for this you can say that your mixedness is 0. For the pure state, there is no mixedness, right? But if it's 1 for the maximal mixed state, right?
What does it mean?
D is the dimension of your space, right? For the normally you have trace of the rho square equal to 1 over d for the maximally mixed state, and d is your dimension of your space.
What about in one dimension?
No, interesting. No, 1 dimension, do we have that? Because normally we start with, I don't think do we have that? Yeah, dimension of Hilbert space. Yeah. Yeah. Like if you consider qubit, you have two dimensions or something like that. Okay, and then next we're going to talk about unitary evolution, right? We know that actually your quantum state can be mapped to a new one through this operator U, right? And then you require this operator U to be a unitary operator, right? In order to preserve the probability distribution, right? Some of the that, and then from this relation, you find that actually your density metric also can be mapped to a new one that I call Plum here, to this kind of formula. Relation is like you sandwich your density metric with the U operator, right? From the left and from the right. Very simple. And we find that the degree of the mixedness is preserved under the unity evolution, right? It means that if you start with the pure state, under the unitary evolution, you still get the pure state, right? But if you start with the mixed state, you end up with the mixed state under the unitary evolution, right? This is well, I would say that this is the key ingredient to understand the paradox later. I will point this out again later, okay? And well, next is about entanglement. Well, entanglement is a special correlation that actually exists in the quantum realm, right? There is this kind of correlation in the classical world. And in mathematical point of view, actually in this talk, I'm going to focus only for the bipartite system with the pure, only with the pure state, because this is relevant to the problem with information paradox, okay? So if I have a state A here that actually belongs to this Hilbert space, right? And then another one that we call B here, and that belongs to this Hilbert space, right? The composite state can be put, I mean, in this product form, right here. And then if you can write down your state in this way, that we call this is a separable state or the product state. Yeah, it's very trivial. Okay, and then your density metric can also be put in this product form as well. And then if you find that your state can be expressed in this way, it's said that there is no correlation between A and B. Okay, but if it's not, then you say that your system, they are entangled, right here. And then there is a correlation between A and B. Okay, to see this, well, more clearly, I give you an example, okay? The first one is separable state. Why is it separable? Because if you look at this, this is a composite state, right? The first bit belongs to the A system, and the second bit belongs to the B system. And then you see that there is a common bit, the 0, 1. You can pull out the common bit 0 here. And then you can say, that is the first one that belongs to the first system A, and the second one belongs to the second system B. This is the product form, right? Then there is no correlation between A and B, all right, here. And the second one is quite different from the previous one, because if you look at this, there is no common term. I mean, there is no common bit here. And then this is known as a Bell state here. And then, if you say that, I would like to try to see whether this can be put in the product form or not. So I start to write a system in this way as a superposition of the 0 and 1, right? And the B as well. And then I do the multiplication, I mean, between A and B, and then I get this equation, and then I compare this one with the first one, right? And then I try to solve for all the coefficients, and then we get this set of equation, and you see that this is not compatible. Right, then it means that this state cannot be expressed as the direct product between A and B, and then you can draw a conclusion that actually your system is entangled. There is an entangled between A and B, right? This is very straightforward computation, okay? And next one, so previously we kind of see how to detect whether your state entangled or not, right? by looking at whether you can put your state in the product form or not, right? Then the next one, the question how to quantify it, right? How much degree of the entanglement in your system, right? And then that is, there must be a measure, and then the measure for that is the Voigt-Neumann entropy here, right? When we talk about entropy, it means that we talk about how much we don't know about your system, right? Yeah. If we know everything about your system, your entropy must be 0, right? But if you don't know anything about your system, then your entropy must be maximum, something like that. Okay, so this is the Voigt-Neumann entropy, and the rho is the density matrix. And then if you can explain, well, if you write your if your density matrix can be explained in what we call the spectral decomposition, right? Here, the lambda is nothing but the eigenvalues of your density matrix, and then you put this rho into this one, and then you find that actually your entropy can be expressed in terms of the eigenvalues of the density matrix. Okay. And there is properties of the entropy. The first one, the entropy is 0 for the pure state, right? Because for the pure state, there is only one state. You know for certain, right? What is your quantum state? Then there is no surprise. Then your entropy must be 0, right? But for the Hilbert space with dimension d, the upper bound for your entropy is log d, right? D is the dimension again, dimension of your quantum state, quantum system, and there is the concavity property of it, and then the main ingredient and the main property in this context is subadditivity, right? Is that the entropy of the whole system is less than or equal to the individual one add up together, right? If you have the equal sign, it means that there is no correlation at all, right? But if you have a less than sign here, it means there is some correlation between your system. And the rho A and the rho B are called the reduced density matrices, right? If you want to compute rho A, you have to trace out B part of your system, right? If you want to compute rho B, you have to trace out the A. That is the thing that, well, very straightforward. Okay, let me give you an example again. Now we start with this composite state, right? Okay, and then, well, it's not difficult to check that actually this one is a pure state. And then if you compute the entropy of the rho AB, you will get 0, right? Well, if you want to check whether this is the pure state, you can start that, you compute the rho AB, and then you compute the square root, right? That is the thing, very simple. But I skip it because it's not so difficult to do it. And then next, you compute the reduced density matrix, right? I mean, this the slash means you can you can compute rho A or rho B, right? By tracing out or B or A, right here. And then you find that actually you get this one, this state. And then if you put this one in the metric form, you will get this one, right? This is P, and then this is P minus 1, right? Right, yeah. It's very trivial that actually these two elements are in the diagonal already. It means that these are the eigenvalues of this rho A or B, right? And then if you want to compute the entropy of the reduced density matrix, you can do it right away, right? Because you know what is the eigenvalue of your reduced density matrix, right? And you get this one. And then it's not difficult to see that this entropy reach its maximum when P is 1/2, right? It's a half. Here, it's not difficult. And then you get this kind of graph again, okay? And then if P is half, then you get the Bell state back. And then the Bell state is the maximal entangled state in this class. I mean, in this bipartite pure state class, okay? But if your P is 1, or P0, you will get this pure state, I mean the product state, right? If your P is 1, you get this one will be gone, right? Here, and then you get this one. This is trivially, and it is very trivial that actually you get product state, right? And then if your P is 0, you get again product state. And then there's no correlation here, then you get 0.
Why the entropy of rho AB is 0? The second line.
This one?
Yes. It means it's a pure state, means it should be product state or no?
Well, it's pure state, but not the product state.
Oh.
Right. Okay. And then it's not difficult to see that this inequality holds for that particular system. And then what we can draw from that from this particular example is that the greater of the entropy of the subsystem, the more correlation between subsystem and thus entanglement. That's what we can draw from this. And then, but the thing is that if you look at the process that I did the computation, I start from the pure state, rho AB, right? And I do the partial trace. I end up with the rho A or the rho B, and then I get the mixed state. It means that this process is not unitary, right here. And then we can say that the mixed state is a part of the pure state here. And again, this is the key message to understand the information paradox later, okay? And it's not difficult to see that actually your entropy preserved, I mean invariance, I would say, under the unitary evolution, right? It's not difficult to see. You can do the computation and then you can check it, and then because this is a consequence that if you start with a pure, you stay with a pure, right? If you start with a mix, you stay with the mix, right? And when the degree of the mixedness is preserved under the unitary evolution here, then your entropy remains the same. Okay, and then there is one feature that we need to understand that called no cloning theorem here. Thing is that so here I have a state C, right? And I would like to clone this one. What I mean by cloning, by what the word clone is that I would like to put this state C into this default state I call 0 here. My 0 state is the default state, okay? And then under the U, the operator U, I can do that cloning by this. I'm going to have another C here, right? That is the operation of the called copying, quantum copying machine, something like that. But okay, if I say that my state C is in the superposition between 0 and 1, right here. And then I look at, so I have to multiply the C with the 0 state, the default state, right? And then I can move this 0 state inside the bracket, right? And then I get 0, 0 here, and then I get 1, 0 there, right? And then I apply the U operator. It means that I can put 0 here into this 0 here. I get 0, 0 there, okay? And then here I can put 1 into this 0 bit here, then get 1, 1 there. At the end, we get this state, right? But, well, if you look at this, the whole thing, it means that if I start with the C state here, it means that I'm going to end up with the CC state, right? It means that if I do multiplication between this CC state, I'm going to get this 4 different, right? So, and then you see that this is not consistent. Then there is no such U operator here in this context. It means that there is no quantum copying machine. There is no way you can copy the quantum state here. Okay. Okay, all right. All right, and then another thing is that they call quantum monogamy of the entanglement. Okay, if you have like a pair of maximal entangle like AB here, they are in the maximal entangle state, right? They will not share the correlation with the third party here in C here, right? It means there is no threesome here in this situation. Yeah. Only these two guys, right? No threesome. This is impossible correlation if these two guys are in the maximal entangled state, right? This is this feature known as a monogamy, all right? Okay. Okay, now we kind of ready to look at the information paradox of the black hole, and I give you all the necessary background for this. So I start with this black hole, and then I am not going to talk about what is the black hole. I assume that everyone understands what is a black hole. Okay, this is my black hole, and suppose I throw a cup of coffee into the black hole, and then what we understand that is that the cup of coffee possesses entropy, right? If you throw a glass of coffee into the black hole, it means that this part of entropy will be disappear from the outside world, right? It's lost forever. It means that this going to give you a trouble because this violates the second law of thermodynamics, right? Then it must be something more. There must be some well, I don't know. Well, and then, well, to solve the problem, Wittgenstein proposed that actually black hole has entropy and is proportional to the area of the horizon, right? And then I put this parameter alpha here because according to the classical context, you don't get the right factor here. The right factor here comes from the quantum context, right? Actually, I think this part of the entropy comes from what they call the black hole thermodynamics, right? Something like that. But I'm not going to talk that on that part. But I believe that someone else will talk about this later. Okay, about black hole thermodynamics. Then, okay. So then now we have what they call generalized second law of thermodynamics, right? It means that the change of the entropy of the black hole plus the change of entropy of the something else outside the black hole has to be increased, something like that. The problem seems to be okay, but if you, well, the thing is that this implies that actually the black hole has a temperature and it must radiate, right? And then in order to understand the mechanism of radiation of the black hole, you need to incorporate quantum mechanics, right? And then Hawking said that the black hole emits radiation at the same rate that the black body would, right here. And then, actually there is a huge computation in order to get this one, but I skip it. But the thing is that this is like an outside observer, which is actually far away from the black hole. So the thing is that this observer will see the thermal radiation from the black hole, and this thermal radiation is actually nothing but a mixed state. And then if you look at this kind of formula here, this is almost look like a black body radiation apart from this factor. There's no, I think the people call it the gray factor, something like that. If I remember, I don't know, maybe, or absorption factor, maybe, because. I think people say that actually black hole is not totally black, right? Something like that. There is this because there is they absorb something and spit out something. And then from this thing you can find out that actually the temperature of the black hole is kappa over 2 pi. The kappa is surface gravity of the black hole. And then once you get it, you can fix the parameter that I put at the beginning is 1 over 4, and then you can find that actually the black hole entropy is proportional to the area over 4, something like that. Okay? All right, and then we find that actually the temperature of the black hole is proportional to the 1 over m mass of the black hole. This implies that the black hole emits particle and it lost energy, and of course it mass as well. And the black hole will get hotter and hotter and emit more and more particle and eventually disappear. This process known as a black hole evaporation, right? And then this causes a problem, you will see later. Why is that? Now I'm going to give you a cartoon version of the Hawking radiation. We can think that actually the Hawking radiation coming from, like, if there is a virtual pair actually have been created around the horizon, right? And then one of them fall into the black hole, and then another one escape to the outside observer here, right? And then this escape particle is called the radiation particle here, right? And then if this process continue, right, but your black hole start shrinking, right, and then you get more and more radiation particle here, right? This guy can collect more and more radiation, and then at the end, your black hole disappears, right? And then it will left only this kind of radiation for the outside observer, right? Which is actually in the mixed state, right? Because it's thermal radiation. So now we kind of ready to see what is the heart of the paradox now. So suppose that you can think this pure state as a radiation, okay? And then when we say this is a pure state, it means that you can compute the density metric, and then you can check that actually the entropy of this pure state is 0. This means that you know for certain what is your quantum state, right? And then this state is somehow have been given to this observer, right? There is no surprise because he knows for certain what is the quantum state, right? This is, I would call this is the direct process, right? And now this is the indirect process, right? This pure state has been put to the black hole first, right? And then something happened later for this observer, right? Suppose that now we look at one radiation at a time, okay? So once you put this pure state into the black hole, and then this one radiation happen, I mean this one fall into the black hole, and then there's one escape to this guy outside the black hole. And then as I mentioned, this pair of this particle are entangled, right? Then they can put the quantum state of these two in this actually the Bell state, because it's quite easy to understand, right? And then we can compute the total state. I mean, this level 1 is mean that one radiation. So the total state of the system is the product state of the pure state that actually fall into the black hole, and the entangled state of this pair particle here, right? And then you can put this one into this formula, and then you can compute the density metric of the whole system, right? Which is a little bit huge one. And then the thing is that this guy, he's outside of the black hole, then he has limit to access all the thing, right? He could not access all the things that actually fall into the black hole, right? It means that so we have to trace out for this guy, we have to trace out the C part here, which is actually fall into the black hole, and the first bit of this state, because this is the first bit actually belong to the A particle, right? Actually fall into the black hole. Then we have to trace C and A out, and then you left only this B. Actually, this is all this guy that can access, right? Yeah. And then you end up with this one, and then you compute the entropy of this radiation, you get log 2, right? It's not 0 now. Okay, you see that? It means that this indirect process, you get not 0 entropy at the end, right? It means that if you put your pure state in the black hole together with the radiation, you will get mixed state, right? Because here is a mixed state, right? But well, we have to, if we continue, like to consider two radiation, we repeat the process again with this one, right? And then we do the same computation again. We have to trace now all the part that actually belong to the inside part of the black hole, right? And then we end up with the entropy that actually 2 log 2 here, right? Yeah. And then suppose that your black hole will be kind of disappeared after n radiations, yeah, right? So you get the total state in this way, right? And then again, if you compute the entropy of the radiation, you will get n log 2, right? So, and then if we plot the graph of the radiation entropy, you start from 0, and then it's increasing to the maximum when your black hole disappear here, right? Yeah. This is quite interesting feature because first we fill the black hole with the pure state, right? The initial entropy is 0. But at the end, when we watch the black hole completely evaporating away, living outside also with a highly mixed state, and the entropy of the final one is n log 2. Well, and then this means that the whole process is not unitary, right here. It's not unitary because it's quite trivial. And of course then, the information about this pure state is completely lost into the black hole, right, from the observer outside, right, leaving only what I call scrambled, mixed, unuseful information. I mean this kind of radiation here, right. This is the way that you can think this is making a paradox, right. What is a paradox here? Okay. So, well, then there is a number of people actually try to solve this problem. Okay, the first one comes from, I think, Susskind. The idea is called the black hole complementarity. Is that the Susskind said that the outside observer, yeah, you see the information accumulate on the horizon of the black hole and come out with the radiation. This is very key, phase here, come out with the radiation, right? And the inside observer will see the information located inside the black hole, right? So, well, this idea, the black hole complementarity requires what we call the holographic principle, right? Because the holographic principle says that the physics of the 3D, interior of the black hole, including the gravity, can be treated as a physics on the 2D on the horizon, right? Well, I think if you fancy about this topic, you can go to this guy, this paper, ADS-CFT, right? Something like it's going quite difficult, I think. But anyway, so it means that the information inside the black hole can be deposited on the surface, something like that. That is a rough idea. And then it's going to come out with the radiation, all right? Okay, so look at this with the cartoon version. For the outside observer, if I say that actually this cup of coffee, I have this string of bits representing the information of this cup of coffee, right? And then this cup of coffee has been put into the black hole. And the information of the cup of coffee will be deposited on the surface of the black hole, right? And once your black hole is radiated, it's going to carry out the information, right? And then the thing is that this thing is for the outside observer, this is not correct. Infalling object is stuck on the horizon, right? That is the point of view from the general relativity, right? And the information will come out with the radiation, like here, right? And then your black hole start to shrink, all right? And then once your black hole is completely gone, disappear, so your information can somehow escape right here with the radiation. That is the idea because it's come out with the radiation. And this is for the outside observer perspective, right? But for the infalling observer, that actually they have another guy actually fall into the black hole with a cup of coffee, and then what she or he can see is that actually there is this kind of information locked inside the black hole with him, with this observer actually. And then the thing is that the infalling observer cross the horizon smoothly, that we know this is called no drama, right? Because the horizon is no special place, right? If you cross, you can cross it without noticing anything, but once you cross it, you cannot return, right? According to the general relativity. And now so you have like two different scenarios here. Right? It depends on who is the observer, right? But if you are the outside observer, the information escapes, right, with the radiation, right, here. But if you are an infalling observer, right, the information actually locked inside with this observer, right? Then but the thing is, even, I mean that it seems to just, this thing seems to suggest that the reality depends on who is the observer, right? If you're the outside one, you have this scenario, but if you are in the infalling one, you have this kind of scenario. But there is no contradiction here, because these two guys cannot communicate, then they cannot talk, right? There is no problem, right? This is what they call complementarity here, right? Okay? Okay, the thing is that now, if you look at this picture carefully, you will see that actually there is two copies of information here. Because there is a copy with the outside observer, right? And then there is another copy, which actually belongs to the infalling observer here, right? And then it seems to suggest that actually black hole behaves like a quantum copying machine, right? But again, there is no problem because these two guys cannot communicate, right? Then they cannot compare the quantum state. Then there is no problem. This is again complementarity, right? Okay. So let me draw a main statement from the black hole complementarity here. The first one is for the outside observer. It means that the information can come out, right? With the radiation, then it means that if you start with the pure state, you're going to end up with the pure state, right? Something like that. It means that there must exist a unitary operator U, which actually describes the evolution of infalling matter to outgoing Hawking radiation, right? There must exist this kind of operator U, right? Otherwise, the information could not escape, right, out to the outside world. And the second one, the infalling observer experiences nothing out of the ordinary when crossing the horizon. This is called no drama, right? This is, actually there are other statements, but I think these two are relevant for this context. Okay, so this seems to solve the problem of the information paradox because actually information can come out with the radiation, right? But there is a group, yeah.
The information that both the inside and the outside observers have, are they the same information or the complementary information?
I think it's, up to this point, I think they are the same. Yeah. But again, they cannot compare, right? Then it's kind of complementary anyway. Okay. So now I recall a graph of the entropy here, and then there is a guy that named Dong Page here. He suggests that if you want to make your the whole process to be unitary, it means that the radiation entropy you start with a 0 one, right? And then it increases with time here. At some point, it has to decrease, right? And end up with the 0 entropy again. It means that you end up with the pure state again, right? That is the thing. It means that and then this particular time we call Page time is a halfway of the radiation. Why is the halfway? There is some argument on mathematics about the structure of the density matrix, but I won't go for that, okay? But there is the argument why it's the halfway. But the first, the argument is in this way. So the first half, the radiation still mixes from the outside observer, but the second half, for the outside observer still, not still, but start to see entangle between this or seemingly random radiation. This is the reason why the radiation start to get purer and purer and then end up with a pure state at the end, right? Okay. And this is the idea. Give us what we call the firewall. There is a group of physicists. One of them is Poshinsky, right? There's some other guys I could not remember the name, but that is the guy that, called Poshinsky. Agree that actually black hole complementarity requires too much, right? Therefore, it gives a self-contradiction because the first, this is another way to represent the black hole, right? Yeah. The first one, as I mentioned, actually the information can come out from the black hole, right? With the radiation, it means that the Hawking radiation is pure, right? Right. And then there exists the unitary operator to describe that kind of whole process. And then we say that actually this is the halfway of the radiation, right? And we call this is the early part of the radiation, and this is the late part of the radiation, right? This is the outside observer. And well, when the evaporation proceeds until after the halfway, so you get this is the early radiation at the location of the outside observer, and then this is the pair creation has been created right after the halfway, and then we know that actually this B and B prime are entangled in the maximal one with the maximal one, right? Yeah. And as I mentioned that after halfway, this outside observer start to see entangle between all this seemingly random radiation. It means that there is a purified process happening here. What I mean by purified means that this guy, this B part of the red radiation start to form the correlation with the early radiation particle here, right here. This B, right, start to form the correlation with the earlier particle here, right. It means that now this is the purified process, right, because actually this is the mixed one, right, yeah. But the thing is that, as I mentioned, this B and B prime are entangled to each other. And then if you look at this picture carefully, you will see that this is a threesome, right? It should actually not allow, right? Then it means that, well, it's, because we know that actually there is a quantum monogamy right here, then this is not this is impossible correlation here. So if we have to choose now, if you want to keep unitary, we have to throw away no drama. What I mean by it means that if you want to keep unitary, it means that you need the Hawking radiation at the end to be pure state, right? It means that this one had to form the correlation between the early radiation, right? And then the correlation between this guy and this guy had to terminate, terminate, right? Yeah. And then breaking up the entanglement between B and B prime, causing accumulate of the energy around the horizon, and then you will get a firewall here. Okay, and then there is a drama now and then this suggests that actually GR has to be modified. I don't know, because normally according to the GR, the horizon is no place spatial, right? But now it's a spatial place because there is a firewall now, right? Yeah. And now we come to the conclusion of the paradox. So, from the argument of the AMPS, a group of physicists say that the black hole complementarity requires too much, right? that two statement cannot hold simultaneously, right? You have to choose only one of them. But if you want to save quantum, it means that you choose unitary process, right? You get firewall here. As I mentioned, as I explained earlier. But if you want to save GR, it means that the information that actually come out from the black hole is not useful. It's a scrambled one. And then there is no unitary process. Then you have to choose which one you need to save, right? Yeah. But that is a thing. Well, and then this would be kind of the end of my talk. But I would like to mention that there is further development in order to solve this firewall paradox. But I am not going to talk at this in this talk. It's called ER equal to EPR, right? The people say that actually the particle outside can still correlate with the particle inside of the black hole to the tiny wormhole. And that tiny wormhole can be viewed as entanglement, something like that. And then they say that if this kind of correlation exists, you don't need the firewall anymore, right? And then again, the paradox seems to be solved, but I don't know. Because we don't have experiment to confirm that actually there is a tiny wormhole that link every single particle that are coming out of the black hole with the inside one. And there is another idea actually that people say that actually the information can come out of the black hole by means of the teleportation. This is kind of very recent development, but I don't know much on that. Then I might give a next talk on this kind of ER equal to EPR and then teleportation of the information out of the black hole. So this would be all for my talk. Thank you very much. Okay.
There are any questions from the audience?
It's too easy, right? Well.
Actually, I have a question for the no cloning theorem. It seems like we have used the assumption that U is linear. I'm not sure why is it important that U has to be linear.
U is a linear one. So normally we need linear operator. What you mean by is that if we have like a nonlinear operator, we could do that. Is that right? I don't know. I'm not sure. Yeah.
I actually don't know if anyone has come up with this nonlinear operator.
No, I don't know, but I can check it later. Interesting. Okay. And yeah. But I believe there will be a talk on black hole thermodynamics later, but I don't know when. And then you guys can, appreciate more on black hole. Okay.
Any other questions? Especially for students.
No, it's
Okay.
really simple. They say, oh, it's easy, nothing difficult here.
Okay, so then no more questions. Then let's thank our speaker again.
Okay, thank you.